We've evaluated induced sign characters at Kaj-down-listic basis elements. Now let's evaluate induced trivial characters at Kaj-down-listic basis elements. Recall that the permanent of a matrix B is the sum over all permutations in Sn of the permutation monomials B1Wn through B1W1 through Bnwn with no coefficient other than 1. So thus, if B is the path matrix of a planar network D, then the permanent of B equals the number of path families of all types, because there's not going to be any cancellation there, from all sources to all sinks. Alright, so what does this mean about character evaluations? Let's let W and Sn avoid the pattern 3, 1, 2. And let's fix lambda, a partition of n with r parts. Then, if we want to evaluate the induced trivial character, eta lambda at the Kaj-down-listic basis element CW, this is equal to the eta lambda immanent of B, which is the sum over all ordered set partitions capital I1 through capital IR of type lambda, permanent of A, I1, I1. So I'm letting A be the path matrix of FW. So permanent of A, I1, I1, product up to permanent of A, IR, IR. Well, this is a sum of a product of permanents, and by our interpretation of permanent, so we have that the permanent of A IJ equals the number of collections of lambda j paths from sources indexed by IJ to the sinks indexed by IJ, but any permutation of them. So we can draw these paths in a tableau. So there's a number tableau of shape lambda in which row j contains lambda j paths and we might as well list those paths in increasing order of the source indices. And then the sink indices are going to be some permutation of those lambda j source indices. So it's sort of a lot to say. So let's call these tableau left row strict. Because every path has a source index and a sink index. And the source index, if we wrote the two indices, the one on the left, the source indices would be increasing just because we're increasing them in, we're listing them in increasing order. So left row strict means that source indices increase. And they're not just left row strict. The sink indices are a permutation of the source indices. So we'll call them left row strict, row closed. So if we look at the sink indices, there's no indices there that aren't already there as source indices. So we'll call them left row strict, row closed, FW tableau of shape lambda. So let's do an example. So let's look at the permutation 1, 3, 4, 2, and FW looks like this. And let's use the partition 3, 1. And I'm going to write in each tableau ij for the unique path from source I to sink j. So there's tableau of shape 3, 1. So things like, let's see, I'll number these to make it easier. Things like 1, 1, 2, 2, 3, 3, 4, 4, if we look at the path family of type E. You know, keeping 1, 2, 3 on the bottom, 1 has to go to 1, that's the only option, but 2 and 3 can swap. So we also have 1, 1, 2, 3, 3, 2, and I'll write them in this order because we have 1, 2, 3 increasing. Now if 1, 2, 3 are in the first row, those are the only two options. Now let's see what happens if we have 3, 3 in the second row and 1, 2, 4 in the first. So an obvious choice is 1, 2, 1, 2, 2, 4, 4. 1 has to go to 1. And actually 2 can't go to 4. It could go to 3, but we already have 3 going to 3. So 2 has to go to 2 and 4 has to go to 4. So that's the only option with 1, 2, 4 in the first row and 3 in the second row. So what if we have 1, 3, 4 in the first row and 2 by itself in the second row? 1, 1, 3, 3, 4, 4. 1 has to go to 1. 3 can go to 4 and 4 can go to 3. So 3, 4, 4, 3 is another option. And that's the only option because 1 can only go to 1. Now if we put 2, 3, 4 in the first row and then 1 by itself in the second row, we'll have more possibilities. 2, 2, 3, 3, 4, 4 is the most obvious. 2 and 3 could switch, so we could have 2, 3, and 3, 2. 3 and 4 can switch, so we could have 2, 2, 3, 4, 4, 3. And then we could have 2 going to 3, 3 going to 4, 4 going to 2. I'll write that up here. 1, 1, 2 going to 3, 3 going to 4, 4 going to 2. So those are all our options. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So eta 3, 1 of C 1, 3, 4, 2 is 9. Now this is one way to do the computation eta lambda of a Kajsteinistic basis element. There's actually another way. And the second interpretation of the permanent of a matrix leads to a second method of computing eta lambda eta lambda of a Kajsteinistic basis element. Alright, I claim for W in Sn avoiding 3, 1, 2. B, the path matrix of Fw. We have that the permanent of B equals the number of row semi-strict PFW tableau of shape lambda. Now row semi-strict means if we have I next to j in the same row, then this means that either I is less than j or they're incomparable. So basically the only thing that's not allowed is we can't have I greater than J in the post set PFW. So to see this, let's let rho be the unique path family of type E covering FW. And by the previous claim, the permanent of B equals the number of path families pi of any type covering FW. Now we said row closed, left row strict, but permanent is eta n of B. So we're looking at a tableau of shape n. So it's got all the paths there. So if we list them in order 1 through n, so if we just write the sequence pi 1 through pi n, it's automatically row strict. It's automatically left row strict. And the sync indices are going to be some permutation of 1 through n, so it's automatically row closed. So we're really just counting path families. We don't need to say left row strict and row closed. All right, let's consider one path family pi of type V covering FW. Let's write V inverse in standard cycle notation. So that is the greatest letter first in each cycle. And then cycles ordered in order of increasing greatest letter. So So this is something so when we write this in cycle notation, it's hard to say where V1 and V2 are, but let's just name the letters X1, X2, etc. These are all, we'll name the letters that we see here X1 through Xn. And now let's drop parentheses. And we'll take this unique path family of type E and write it in the order of row X1, row X2, row X3, etc. All right, this came from a left row strict, row closed tableau, and we claim that this gives a row semi-strict PFW tableau. So since row has type identity, its component paths are basically the elements of the post set PFW. So we just need to show that it's row strict. So we need to show that it's row semi-strict. So assume that we have row xi greater than row xi plus 1 in the post set PFW. So these would be consecutive in that list. So if we have that, that means that there is no path in FW from source xi plus 1 to sinks xi. Now, if xi plus 1 and xi belong to the same cycle of V inverse, but they would also belong to the same cycle of V. So if they're part of the same cycle, then we have, let's see, xi came before xi plus 1. That means that V inverse xi equals xi plus 1. Or equivalently, V xi plus 1 equals V xi. oops, v xi plus 1 equals xi. Now we're assuming we have a path family of type v. So that means that there is a path from source xi plus 1 to sink xi. But I think that contradicts something we said. There is no path from source xi plus 1 to sink xi, so that's a contradiction. So let's suppose xi and xi plus 1 do not belong to the same cycle. So if they don't belong to the same cycle, but they're consecutive in the standard cycle notation, then xi must be last in its cycle and xi plus 1 must be first in its cycle. But since the cycles are listed with the greatest letter first and in order of increasing greatest letter, that means that xi plus 1 is greater than everything in this cycle. So that means that xi plus 1 is greater than xi as an integer. Now this contradicts rho xi being greater in the path post set of FW than xi plus 1. Because greater in the path post set means that rho xi is up here and rho xi plus 1 is down there, but we're numbering these from bottom to top, so that's impossible. This has to be xi plus 1 has to be less than xi in order to have this relation between them. So that's a contradiction. So therefore we cannot have rho xi being greater than rho xi plus 1 in this sequence of paths. That means that the sequence rho x1 through rho xn is rho semi-strict. Actually, that's only half the proof, because we have to, that's sort of one direction of the bijection. We really would have to do the other half, but I'm going to omit that. If we really did that, then it would be QED. All right, so let's do an example. Let's do the same example we did before. So n equals 4. W is the permutation 1, 3, 4, 2, which has this descending star network. And we're going to be writing row semi-strict PFW tableau, so we might as well write the post set down. This is FW. PFW is, so 1 is less than everything. 2 is less than 4, and both of those are incomparable to 3. 3 touches 4 and 2. But all three of them are greater than 1, so this is the post set. So the row semi-strict PFW tableau. Now I don't need to write 1, 1, 2, 2, etc. because now we're only looking at paths that go from source I to sink I. The source and sink index are the same. So we have, oh, let's do lambda equals 3, 1 like before. So we could put 1 by itself. Oh, let's see. First thing we did before was had 1, 2, 3 in a row and then 4 by itself. So let's have 4 by itself, and we could have 1, 2, 3. We're also allowed to have 1, 3, 2. 3 is greater than 2, but since they touch, they're incomparable in the post set. So 1, 3, 2 is permitted. 1 has to go first in that row because it's less than 2 and less than 3. If we put something greater than it first, then we wouldn't have row semi-strictness. Alright, so how about if we have 1, 2, 4 in the first row and 3 by itself? So 1, 2, 4. And actually that's the only order we can write 1, 2, 4 in, because if we do it in any other order, we'll have greater element in the post set followed by smaller element in the post set. Alright, so we could have 1, 3, 4 in the first row and 2 in the second row. 1 is less than 3 and 4, so it definitely has to come first, but 4 is allowed to come before 3 because they are incomparable. And that's all we can do with 2 by itself. And then if we put 1 by itself and 2, 3, 4 in the first row, 2, 3, 4 can be written in that order. Also 2, 4, 3. Also 3, 2, 4. Not 3, 4, 2 because 4 is greater than 2 in the post set. And we could also have 4, 3, 2. Not 4, 2, 3 because 4 is bigger than 2, but 4, 3, 2 is okay. Alright, and I think that's it. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means that eta 3, 1 of C 1, 3, 4, 2 is 9, which is consistent with what we computed last time. Just one note I want to make. So we proved a result about the permanent, the second interpretation. We proved it for the descending star network of a 3, 1, 2 avoiding permutation. But actually, what we proved is true in general. So with more work, we can show that for a planar network D, so not necessarily a descending star network, and its path matrix A, we have that the permanent of A equals sum over all path families pi of type E times the sum of, for all pi, the number of row semi-strict